Hi everyone! This video looks at a strong base titrated with a strong acid, and we'll focus on the pH calculation before the equivalence point. When the titrant volume in the problem is more than 0 milliliters, then we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to calculate the pH from that information. In this sample millimole table, we are only looking at the E row. Here, we see that the OH- is greater than 0, which means there is some remaining. But the H+ goes to 0, which tells us that it is used up. This situation puts the reaction progress in region 2 of the titration curve, which is before the equivalence point. To calculate pH before the equivalence point, we first have to calculate the hydroxide molarity, and we get this by taking the millimoles of OH- from the E row and dividing by the total volume. We get the total volume by adding together the milliliters of base and acid given in the problem. Once we have OH-, we can calculate pOH by taking the negative log of the OH-. Then calculate pH by subtracting pOH from 14. In our example, our HCl titrant is greater than 0 milliliters, so we know that we need to set up a millimole table. So the first thing we have to do is calculate the millimoles of our hydroxide and our H+. So starting with the hydroxide, we have 15 milliliters of solution. And we're going to multiply by our molarity, which is 0.2500 moles of OH- over liter of solution. Liters of solution will cancel, and that will give us millimoles of hydroxide. For our sig figs, we have 4 sig figs in our volume, 4 sig figs in our molarity, and so our millimoles will also be rounded to 4 sig figs. Doing the math, we have 15.00 times 0.2500 rounded to 4 sig figs gives us 3.750 millimoles of OH-. Doing a similar calculation for our hydrogen ion, we have 11.32 milliliters times the HCl molarity, which is 0.2000 moles of H+ per liter of solution. I'm using the net ionic formulas of hydroxide and H+ instead of the full formulas of the base and the acid, just for simplicity, as you'll see when we get to the millimole table. Checking sig figs, we have 4 sig figs in our volume, 4 in our molarity, and so our millimoles of H+ will also be rounded to 4 sig figs. So doing the math, 11.32 times 0.2000 gives us 2.264 millimoles of H+. Our next step is to set up our millimole table. So we have hydroxide plus H+ going to water. We set up our rows, ICE, initial change, and end. Our units are millimoles. And then we enter our values from the first step. So our hydroxide was 3.750 millimoles, and our hydrogen ion 2.264 and we'll just draw a line through the water. Subtracting the smaller number, we subtract 2.264 from each reactant. That means our hydrogen ion goes to 0, and subtracting for our hydroxide, 3.750 minus 2.264, rounded to 3 decimal places because of subtraction, gives us 1.486 millimoles. Our next step is to calculate the hydroxide ion molarity. So we take our 1.486 millimoles from the E row of our millimole table, divided by the total volume, which will be 15 milliliters plus 11.32. Checking our sig figs, we have 4 sig figs in the numerator. After we do the addition, we'll still have 4 sig figs in the denominator. So our hydroxide ion molarity gets rounded to 4 sig figs. So doing the math, we have 1.486 divided by 26.32, rounded to 4 sig figs, gives us 0.05646, and that's molar OH minus. We can then calculate POH by taking the negative log of 0.05646. We have 4 sig figs in that value. We'll get 4 decimal places for this calculation after we do the log. So taking the negative log of 0.05646 gives us 1.2483 for our POH. And our last step to calculate pH, we have 14.00 minus 1.2483. Our 14 is not exact. It has 2 decimal places. We have 4 decimal places in our POH. So our final result will get rounded to the fewest number, which is 2 decimal places. So 14 minus 1.2483, rounded to 2 decimal places, gives us a pH of 12.75.